Hello. Good morning. It appears the bits and bytes might be moving around. At least possibly moving. Okay, it looks like we might have data. Looks like the levels might be okay. Maybe I'll boost myself just a little bit. I'm not feeling projecty today. Let's try that. Maybe a little more even. How about that? Maybe just a little bit more. Needs more boost. Let's see if that's enough now. Still more boost. Okay, now maybe you can actually hear me. Yeah, okay. Good morning. My name's Ben, AB4EN, if you're an amateur radio operator. And this is Stray Capacitance, where I ramble on about things I don't know nearly enough to be talking about. Hope everyone is doing well in the strange new world we live in. I was feeling unmotivated this morning and thought a good way to force myself to get a little something done on this rainy, dreary Saturday in the Midwest, or Sunday. I don't even know the day anymore, as many of us seem to have reached that point where the days just kind of all blend together. But trying to get something done on this Sunday, and I decided that perhaps forcing myself to do a little streaming would be good, and have the, added accountability of people watching me. So, as I tend to do, first I'll talk for a few minutes about my projects, of which there are always many. So, theoretically, you're seeing my bench now. The bench cam will be a little laggy today because I changed my offset settings in preparation for spending most of the day on the computer. So, I apologize if my hand motions don't match my words too well, but that'll just be temporary while we're talking about projects on the bench. First up, I talked about this a little bit in a previous stream, but I've made some progress on several different fronts. So we talked in a previous stream about these wonderful Logitech trackball sensors. Sorry, my lighting is suboptimal today, isn't it? Let's see if we can improve that. There we go. And these are some of my favorite pointing devices. And my brother-in-law requires assistive technology. Trackball like this, which was also his preference after Microsoft stopped making their version of this. So, in an effort to make his life a little better, I made some pointing device using an NRF 52840. Actually, the Adafruit Feather Express NRF 52840, and did it with one of these little Xbox joysticks, right? And that works well enough, but it's not very precise and it's not very fast. So it kind of fails on both fronts there. And so he and I were talking, and Which is kind of ironic. Let me find my headphones. Oh yeah, there's some nice hiss in there, isn't there? Is that resolved now? I apologize for the buzz there for a couple minutes. I must have bumped the preamp, which is the main topic of the day. And so you probably couldn't hear me for a couple minutes there. Well, I'll recap the last few seconds. So I've got this NRF 52840 board that I've been working on for my brother-in-law for a wheelchair-mounted trackball, effectively wheelchair-mounted pointing device. Right now, I've got one using a little thumb joystick, like the surplus Xbox 360 joysticks, and he would prefer a trackball. And either way, the feather that I built the prototype on is missing a few features that would be nice to have. So I had spun these boards last year, and they didn't work when they tried to initialize the Bluetooth stack, and so I've been working to figure that out off and on. And a couple weeks ago, maybe last weekend, I finally got to the bottom of it. Kind of got the whole mental stack loaded for debugging code with the JLink, using GDB while it's live, getting the right binaries loaded so that you can cross-reference back to the source, all those things, and dug down into the source code of the Adafruit libraries and where it's calling the actual soft device. And of course, as I knew, this wasn't like a problem with the Adafruit software or with Adafruit's design. It was definitely with my design. And actually, part of the hang-up for validating all this was confirming that, right? It's always nice to have a working example when you have a problem. And so in an effort to do that, I finally bought an NRF, like the dev kit for this chip. It was $50, has a built-in JLink. So I kind of had duplicates of every piece at that point. If it was somehow my JLink not working, which was obviously not the case, but you can't rule anything out, I'd be able to use the JLink on the dev kit. If it was my NRF board not working, which of course it was, I could confirm that by loading the code onto the dev kit and seeing it run there. Just kind of giving me all the pieces I needed. So in case anyone ever stumbles on this and is having a similar issue, my underlying problem was that I had taken the Adafruit board definition and I was using their board definition, which is totally fine. I had kind of designed around that constraint just to kind of minimize the number of things I had to do. And part of their board definition was it assumed it had an external crystal low frequency oscillator. Also fine. I designed and built that on this circuit board. You can see the, I need a pointing device. we'll go with this piece of steel rod so that I can short something out. It'll be excellent. You can see the crystal there and the capacitors that go with it, and a little extra capacitance, of course, on there. Well, I have screwed something up in that design. I'm not quite sure what. The extra capacitance didn't fix it, but the low frequency oscillator doesn't come up. And I'm not quite sure of the right way to debug an LFO like that, but that was the fundamental problem. When I went to initialize the soft device, it went to spin up the low frequency of the oscillator because that's how it was configured for the Adafruit board, and that would fail and hard lock the chip because it was just waiting for the crystal to come up and become stable, and it was neither of those things. So after digging into that, once I knew the problem, the soft device can also be initialized using the internal RC oscillator. I switched 1 pound define over to do that, came up immediately, worked beautifully. So that was good learning. I understand now a lot more about the things that can go wrong there, what the problem was, how to debug the problem more importantly, right? If you're a relatively new software developer, debugging is one of those skills. They love to tell you that unit tests and integration tests will save your life, and don't get me wrong, they are excellent. They will save you so much time and so much energy. But at the end of the day, something is going to break in a way that you didn't expect, because if you expected it, you would have coded around it, right? And same here. This is an area in which I am not even remotely an expert, but you need to be able to, my goodness, I'm having all the troubles today. There we go. It looked like my webcam wasn't updating, which it probably wasn't. So again, now in addition to the sound not working, you probably weren't able to see where I was pointing. Anyway, this is the board in question. Here's the JST. Here's the trackball associated with it. And yeah, so here's the crystal, the capacitors that go with it to give it the right capacitance for the low frequency oscillator. Not working. Possibly not close enough to the chip, although that's a pretty short run, maybe because the two tracks are slightly different lengths, they're getting different capacitance to ground, and that's throwing things off. I'm not sure. I don't know enough to figure it out. But I know enough that, like, turning it off will let things work. So, we've got that working now, and that will let me move forward with this project and actually get to some of the interesting mechanical design pieces. I have a couple of these trackball sensors available, and as you can see, they're kind of large. I mean, this is almost golf ball size. If I remember correctly, it's about 35, 36 millimeters in diameter. Never go anywhere without your calipers, or people will accuse you of making stuff up. These are, of course, the world's cheapest calipers. 34 on the nose. So it's a reasonably large trackball. My brother-in-law also expressed some interest in, you can go on Amazon and find these small trackballs. They're designed to be kind of held in your hand and driven with your thumb. So here's the marble for it. And this is, I believe, 20 millimeters, 18.95, but I'm almost certainly fat fingering that. Yeah, there we go. Might also be a little bit out of round. It's clearly a glass marble. This is very solid compared to this. The density is much higher. So we had expressed an interest in this, mostly for how much space it takes up. So I've been doing a little CAD around trying to find a good way to hold that. There are some of the various prototypes, and of course I've printed it out in like a translucent, neon green or yellow, which of course photographs beautifully, but so it goes. So I'm working somewhat on that. The sensor that I'll use with these is up in the air. Since I've gone through the work of reverse engineering the Logitech sensor, it would be nice to use it. And these do come off the back here. They do just pop off. There are a couple clips. But of course, holding that in a 3D printed enclosure on an FDM printer will be a very interesting experience. 1 second, please. A friend just told me that my video is hung again, so we'll transition the camera off, transition it back on, and there we go, back to life. Thank you very much, Matt. So anyway, we'll be off the bench cam here in a minute, so hopefully that will make things a little better. So here's the small trackball, trying to figure out how to get the sensor in here, or I'll have to design around the new sensor. The other interesting challenge is this is kind of the main body of the, here's the previous version of the pointing device, and it's designed to mount underneath the right armrest, so he can drive it with his right hand. So if you rotate this 90 degrees in your mind, that's kind of what we're going for. And this edge lines up with the edge of his wheelchair arm. So I can kind of move up there. And that's what you'd want, right? Because it's, the wheelchair arm is reasonably thick. You'd want your thumb to kind of rest on the trackball. But there's, 30 or 40 millimeters of vertical difference there. So I'm playing around with some ideas of a little ledge. This could be moved up, and obviously will be in the next iteration, so that it moves the trackball up here. But that will kind of result in a big nodule here, for lack of a better word, that will get somewhat in his way, right? He has to get in and out of the chair several times a day. We did design this like slide-on mount, so it's reasonably easy to remove this, but of course it'd be better if you didn't have to. So lots of interesting challenges there. So that's one thing that's just kind of on my bench, and there are several others. I actually kind of did a virtual hackathon with some friends yesterday, which was a whole lot of fun, and got to play around with some machine learning stuff. Didn't make a huge amount of progress. The goal is actually to build a neural network that can do hummingbird recognition in real time. I enjoy feeding hummingbirds, and once the weather gets just a tiny bit warmer, I'll have a total of about 9 hummingbird feeders scattered around our property. And what would be really wonderful would be to have webcams on all of them, and a neural network running to let me know when there is a bird, an individual feeder, maybe switch the feed. Possibly that turns into something like a YouTube live stream that would, focus on the feeder where the birds are. But that's not the project for today. That was the project for yesterday. And I made some progress, but have a lot left to learn. Now I'm going to move the headphone amp at great risk to our sound quality. The bar is still moving, so I think we're okay. So this is actually the project for today, which is what my audio is coming through right now. So this is definitely stuntman level streaming, where I'm streaming about the hardware that I'm streaming on. Seems like a terrible idea to me. So this is a headphone amp that I put together a little while ago, and I talked about it a little bit in an earlier stream. I've got a Shure SM58 for my microphone here, which I like quite a bit. I think the sound quality is quite good, and more importantly, the directionality is good. It doesn't pick up the HVAC or the cats quite as much, or other things. But as you can see, this is kind of just chucked together on a breadboard, and I really need to lock this down and get this a little bit more stable. In addition, I'd like to get a power LED on here, because it'd be nice to get an indication that it's working, which it appears to have stopped doing just now. Is it working now? Now I think we're back to working. So as I was saying, it'd be really nice to get this stable so that it worked reliably, rather than me having to fiddle with it every time I wanted to stream. It's certainly, just that little bit of friction that makes you not want to get things going. So my goal for this morning is to do some schematic capture here, probably have to create some footprints, and maybe do board layout. As the quarantine and lockdown goes on, it's nice to have a few things planned out in advance, and I've got a DigiKey order almost ready to go. And I always hate clicking the order button on those because you always wind up missing something. But so the goal today is to capture all this and hope probably take out some of the, when I was debugging this, you can kind of see I threw capacitors at a lot of problems that probably aren't necessary. So we can probably remove, I don't know, half the capacitors that are just across the power rail as I was trying to figure out what the heck I was doing. And capture the important values, capture the voltage splits that we're using to bring this up. So this currently has a 5-volt power supply. Now, apparently I'm waking up because I'm projecting a little bit and I'm starting to nail my levels. Well, fine. Let's see if that's a little better. So 5-volt power supply. So to bring it up into the middle, we kind of use a voltage reference. We split the voltage in half, so 2.5, and then we amplify around that. So we'll talk through the circuit a little bit more as we capture it, which means it's time to go to the desktop, where hopefully the lag will not be nearly as annoying. Okay, so what have we got here? We've got KiCad. Apparently it's pronounced KiCad. I will probably mispronounce it as KiCad several times because habits are hard to break. We've got some slightly cold hot chocolate to hopefully help wake me up. And boop. It helps if I click the transition button. So we've got KiCad. I just said I would mispronounce it, didn't I? And we've got some data sheets here. So I've got another project that I also need to do board layout for. I've pretty much finished schematic capture on it. And in it, after some research, I started it off with some LMC op amps, and after some research, I wound up with some OPAs, OPA 1678s. And they seem to be audio optimized op amps. So the first thing I want to do this morning is kind of look at this and see if this is more or less a drop-in replacement, because it would be nice to build this circuit with the same op amp as the other one, just kind of one less thing to worry about, right? And then I can take any lessons learned from one and apply it to the other with a little bit more confidence. So in screwing around with these circuits, the most important things seem to be, well, there's the voltage requirements, and op amps generally have a pretty wide voltage range. They're often specified as single or dual power supply, but every op amp is really kind of the same in my understanding, in that what you need is the voltage range, right? If it's specified as it is over here as plus or minus 2.25 volts, right? What that really means is as long as your high rail is at least 4.5 above your low rail, you're fine. You've got enough power. And they say that here, right? They kind of specify it as, here's the dual supply layout, and here's the single supply layout. For ease, and because I'm lazy and I really don't know what I'm doing, I'm going to use the single supply layout with a 5-volt supply, and simply move my signals to the middle. So both of these are what get classed as rail-to-rail output op amps. That means that generally speaking, your signal can move very close to your power rails, sometimes even a little beyond, depending on which rail and which op amp. But the important thing is staying the appropriate distance away from your op amps, or from your power rails, and getting the right offset into that. So let's get a little bit going with our schematic capture, because some of this doesn't matter. Nice blank page. We'll start here. And we will start off, and hopefully it finds all my connectors. VVH connectors MISC. Perfect. So I ordered some of these tip ring sleeve, sorry, other way around, tip ring sleeve jacks, and as is often the case with electronic components, it's cheaper to order larger batches. So one of the reasons I'd like to use the same op amps on this project as on the other is I ordered a bunch of them because it was literally cheaper to order more than less. So if we think of this as the input and the output, and we will edit this and just call this audio, we'll call it mic in, make it clear. And this one we can call mic out. And we're basically done. We just have to fill in the middle, right? I mean, we know that the lines are going to connect together and everything's, the signal's just going to flow and everything will be fine. So all we've got to do is figure out what goes in between here. I guess we can do a 2.5 millimeter, let's see, barrel jack. There we go, DC barrel jack. Not with a switch. DC barrel jack. Perfect. We also know we've got some power. And just kind of from a mental layout point of view, the mic is kind of in my head, the mic is kind of the special part of this, right? The mic has very low power requirements. In this case, I'm using a dynamic microphone. It has no bias requirements, and the signal levels are very small. And on the PC side or the output side to your mixer or whatever your audio capture device is, the signal levels are kind of higher. So in my mind, this is kind of the layout. And we'll define a ground here. And we'll wire it up to our power. That didn't go the way I wanted it to. Let's zoom in. There we go. Find that a little easier to read. And we'll call this plus 5 volts. I am 100% sure that people who know what they're doing know what all those different plus 5 volt symbols mean. I am not that person. And because this looks a little messy, nope, I'm not gonna do it that way. Maybe I'll grab this one, see if that works. Here we go. That's still very messy. Do that maybe? There we go. That's messy. I don't love it, and actually, so let's move this kind of out of the way. It's not very interesting. But while we're thinking about power, and maybe we'll put a box around this area and just call it power. Double click. There we go. We know we're going to want some decoupling caps. So we're going to copy, duplicate. The one thing I don't love about KiCad, and it's not KiCad, it's me, right? But KiCad has a lot of different keyboard shortcuts, and that's great. But they differ between the different parts of the application. And this isn't new. I'm not complaining about anything that like people much more intelligent than me haven't complained about. But it is one of those things that gets me every single time. So, as a general rule in electronics, you're going to want some power supply decoupling. And normally I'd put this so that it was, there were wires in here, but in this case, I'm actually going to delete. So, something I get to learn as I go through all this. Oh, goodness, I grabbed too much. One of the interesting things in life is it's all signal processing at the end of the day. Your ears are doing signal processing, your eyes are doing signal processing, your brain is taking these signals and running filters over them, and low pass and high pass and band pass and notch filters to get anything out of the world that makes any sense. And if you're interested in this, Vi Hart has an excellent video on how you actually hear and how your ear itself is doing a Fourier transform to find signals in the just kind of random vibrations that your ear is getting. So, especially with op amps, which are operational amplifiers, it's important to understand that signals in the power and signals in the signal are indistinguishable to the operational amplifier, right? It can't tell. How could it tell? It's meaningless to signals and noise are value judgments we place on them later. There is no fundamental distinction. It's just a signal, right? There are signals we want and signals we don't want, and that's the distinction. We call signals we don't want noise. So this power supply that I'm going to plug in here has some noise. Right now I'm actually using an old Motorola cell phone power supply because I went through all my 5-volt power supplies and this was the one with the least ripple on it. And the wires on it are about, I don't know, 1.5 meters, 5 feet, something like that. Let's just switch units arbitrarily. It's more fun that way. They're some length long, and I also live about 2 miles from a fairly low power but reasonably powered AM broadcast station. I think they're 5,000 watts during the day and 3,000 at night, something like that. It might be 1,000 at night. The result is that I've got a 5-foot long antenna pretty close to a fairly powerful broadcast station. And so it's going to pick up signals. And I just noted that Matt is actually in the chat. Thank you very much, Matt. Let's see. Okay. And he's telling me all the things that I'm screwing up. So, sorry, Matt, I'm about 7 minutes behind on your comments. I will pay more attention, and I will go back now and address them. So, up here on the data sheet, Matt asked, when we say rail to rail, is that the input or the output? And it can be both. At the end of the day, it really means the output, but you can have an op amp set up for unity gain so that it doesn't actually provide any amplification. You can also have it set for negative gain so that it is an attenuator for the signal that's coming in, right? So what really matters is if you try to drive beyond the power rails and the output signal flows beyond the power rails, then the op amp will either clip, right? And clipping is real interesting. Maybe I'll talk about this some other time. The more I learn about like ham radio, and again, kind of going back on signals, everything is a signal. And if you take a sine wave and you chop off the top and the bottom, you clip it, right? You get a different set of frequencies. And fast Fourier transform is fundamentally one of those things where it's a real interesting view on the world, and I don't understand it. And good Lord, I do not have the math to understand it. I wish I did. I wish back in college I'd just taken a bunch of signal processing and math courses and actually focused on them instead of whatever it was I did in college. But if you take a sine wave, we'll use these as an example. And let's say this is at 1 hertz. Hello, can we zoom? There we go. Now we got zoom. Let's say this is at 1 hertz. And you chop it off, right? Let's say we chop off this last gradation on the top and the bottom. What you get is a sine wave at 1 hertz minus something to get rid of this part of the signal. What comes out the far side is a sum of different sine waves or cosines, depending on phase shift and all kinds of things, blah, blah, blah. Smarter people than me have talked about this. W2AEW has a bunch of videos on YouTube talking about signals and ham radio in general, but he does some great demonstrations with some wonderful test equipment that he owns, because I believe he works for Tektronix, to show how you build up these signals. A square wave, a wave that goes from 0 volts up to 3 volts over some length of time and then down to 0, is what that really is in the real world, is the sum of all the odd harmonics of the sine wave. So if you take the sine wave, the even harmonic is that times 2. The odd harmonic is that times 3. So 3 times shorter. So if this is the halfway or the quarter way point on the sine wave, right? This is the halfway point because we go through 360 degrees. A times 2 of it goes through that same distinction in half the time. So it would go something like this. And reach its 0 from the bottom as this one's coming through here. If you add those two together, you're going to get constructive and destructive interference, right? If you take the third harmonic of this, it goes through it in 1/3 of the time. So it's going to be somewhere around here, and it's going to go through its whole thing in that time. And you can kind of see a third harmonic would be up here, so it would be adding through this part of the cycle. Down here, which means it would start to chop off. It would subtract from it here, and then as it came back up, it would still be subtracting, but less so and less so as this is coming down. And you can kind of see how that would square this up a little bit. It would bring this corner up, and this edge would start to taper off a little bit as the third harmonic went negative, right? And if you add the 5th and the 7th and the 9th and the 11th and literally the infinite set of odd harmonics to a sine wave, you get its square wave. Same period, but the signal goes from 0 straight to max, straight back down to 0, assuming we're doing 0 referenced and not like a ground reference halfway in between. So just to get that out of the way. So this is true of literally every signal that exists. Every audio signal is some sum of different sine waves or cosine waves, depending if you want the little bit of phase shift in it, right? And that's the fundamental truth. That's what the Fourier transform does and what the fast Fourier transform embodies. So that's right. I was talking about noise. I'm the worst for just going off on tangents. I should take notes when I push the stack. So if you exceed the rails on your op amp, it can't output more than what you give it, except some op amps can go like a very small amount beyond 1 dB or 2 dB beyond the rails. I think they're called over-the-top op amps for literally going beyond the rails, but they are very limited in what they can do. So the important thing is with any op amp, you want to keep your signal between the rails and your output signal between the rails. And that's the fundamental limiter on the gain that you can have. So if my signal, my notes for this project, which may be incomplete, please don't anybody take these as like actually useful. There are different kinds of microphones. One is an electret, and its voltage is around 225 millivolts peak to peak. The microphone that I'm using is a dynamic, so absolute max is around 50 millivolts peak to peak. A line out is a little under a volt peak to peak. So there's roughly an order of magnitude and a half between the dynamic and the line level that I want. So you can see I did a little bit of math here. If I want mic output levels for the PC to consume, I need 5 times gain. If I wanted line out, I would need 18 times gain. And then I did the math also for an electret microphone, which also would require some bias, which I don't believe I have not built into this circuit, I don't believe. So I may add that before I actually send that off, but I probably won't do that this morning. So, hopefully that little ramble about op amps was interesting. And signals, which takes me back to signals. So the op amp fundamentally doesn't know if you wiggle its power rails. It doesn't know that that's different than wiggling the signal rail. They're referenced to each other. So it's very, very, very important with op amps to put bypassing capacitors on your power rail. And I was kind of rambling about signals before. These values they're arbitrary, but they're not arbitrary. Every frequency, what we're effectively building here is a low pass filter for the power rail. We want capacitors, pass frequencies, apologies, capacitors block change above a certain frequency relative to their value. I'm sorry, they pass the signal, and in this case, passing the signal, say the 5-volt rail were wiggling some. Above a certain value, they would pass that to ground, and then the 5-volt rail would stabilize. So the bigger the value, the lower the frequency that it passes, the higher the capacitance. And so slapping a 10 microfarad and a 0.1 microfarad cap between the power rail and ground should be enough to filter out any irritating signals in that power rail, so that we're not amplifying the radio station near me that's coming in on the power line that's also an antenna, but instead we're magnifying my melodious tones through the op amp into the PC, and we're getting what we want and not whatever crazy people are talking on the low AM bands on Sunday morning. And that was actually one of my problems with this circuit as I was learning and putting it together, was I was getting the radio station. And it took me a while to understand what was going on there. So, so some of the component values and things, and some of the extreme amount of bypassing capacitance I did here was due to all of that. And once this breadboards are kind of very useful for prototyping, but each little segment of the breadboard is also a little antenna. Everything is an antenna. Some things you actually want to be antennas. I listened to a podcast called Embedded.fm about embedded software development, and the host Alicia White, hostess, and her husband Christopher White occasionally talk, and she has a quote in particular that's always stuck with me. Everything is a temperature sensor. Some things you actually want the temperature sensor, and some things will also detect other things, but everything will change with temperature. Both of these capacitors are in fact temperature sensors because their capacitance changes with temperature. If that was a signal that you wanted, you could pull that out of just a capacitor on a set of leads, but there are better temperature sensors. So everything is an antenna. Some things you actually want to be an antenna. In this project, we don't want any antennas. So the goal is to bypass out any signals that are going to act as antennas. That was a lot of rambling. What is my part number? OPA 1670X. It's an operational amplifier. You are right. And I believe it was the 1678 that I used in the other design. 1678, which means I've got a box of them. And op amps are kind of interesting. They have multiple. The way KiCad does this is KiCad. My goodness. KiCad does this. Most op amps they come in different packages. So you get one power supply, and then you get multiple individual operational amplifiers built into that. So first thing we need is to give this thing some power. And we can pull that down here, and we'll maybe copy this block, copy block. Did I click it? Copy. Apparently I am too dumb to copy block today. So we are going to give this power. And something I've slowly learned over time with KiCad, if you're interested in KiCad and working with stuff, you can drop these items right on top of each other and it will connect them. The disadvantage to that is if you want to like grab things and move them around, they won't stretch. So now if I grab this power thing, you can see that the power lines will stretch and it doesn't move those signals. And generally speaking, that gives you a little more flexibility. So you see this is U question C. U means a microchip, right? And question mark means we haven't annotated the schematic yet. C is which portion of the microchip we're talking about. So in this case, C is the third section of that OPA that we added. And we can just use recently added here. So if we're going to need both sections here. So we're going to go to recently used and do unit A, unit B, and unit C. I'm going to put unit B down here for reasons that will hopefully become clear. These are three portions of the same microchip. So they all will be wired into the same physical piece of silicon on the board. The traces will all flow together. But for the schematics point of view, you can move them around however you want. And that's actually very, very handy. It took me a little while to get my head around it. But generally speaking, particularly with op amps, you may or may not want, they may or may not be linked in feature. You can put two totally different signals through the two half of these op amps. And you, as long as you understand that there's a little coupling between them, and if you put a very high frequency signal through one, that might show up a little bit on the other, especially if it's a very loud signal, that kind of thing. You frequently want to do different things with them, and we're about to do that. So one thing that an op amp is good for is it's a buffer. I'm talking a lot about op amps today, my goodness. So frequently in life, you find you need a reference. And maybe you need a reference because you're applying for a job, or maybe you need a reference because you don't know where you're at and you're going to stop at the gas station and ask for directions. Sorry, that's ridiculous. Of course you wouldn't do that. We've all got smartphones now. But frequently, you need some point of reference. Maybe you need a time reference to know exactly what time it is. Well, that is true in this case as well. So we're going to need a voltage reference because we kind of talked a little bit that the op amp will go rail to rail, but it can't go beyond that. Well, the signal that's coming in from the microphone here is referenced to ground. It's going above and below 0 volts. It might go up 25 millivolts and down 25 millivolts, something like that. But it's referenced to ground. And we can't do that. This op amp, its positive power rail is at 5 volts and its negative power rail is at 0 volts. It can't go below 0 volts. If you go below 0, it will just clip the signal, you'll get 0 out, and then you start to get harmonics and distortion and clipping. And all those words that people who care about audio use are just names for screwing up your signal, adding harmonics, subtracting parts of the signal, filtering out things you don't want to do. So our microphone here is coming in and is giving us a signal referenced to ground, which is totally cool. And we need, first of all, we do need to reference it to our ground because, you know, saying ground like there's one ground in the world is ridiculous. Now we've referenced it to our ground, and we've done that with the shield on the microphone. You could literally wire this backwards and not worry about it. But in our case, we're going to do it this way because it's the only way I can think to do it. So we take our 5 volts, we resist it with a 10K resistor, we resist it with another 10K resistor, and we go to ground. What are we even doing? We're just going to pass a little current to ground, right? 10K, 100K, it doesn't matter, as long as the two values are the same. But the result of this is that, nope, not what I wanted. We get a reference out. And I'm just going to call it ref, which is probably a terrible name. This signal right there, oh my goodness. It's misaligned. Is that symmetrical? I think it's symmetrical now. Okay. This reference voltage now will be 2.5 volts, halfway between 5 and ground. And you can do the math to figure out how much current this can source and all those things. But this signal will be exactly halfway between these two. And of course, as we discussed, our power rails might wiggle a little bit. That's what our decoupling capacitors are for, to get us a solid reference here. And I note that, I always keep forgetting that, like, I've got a nice big monitor, and then you guys are probably watching on like a screen or something. So hopefully that's a little bit better and you can see a little better. I've even got a tablet in front of me that I can barely read anything on, and you'd think I'd remember that. So we've got a reference level now of 2.5 volts. Well, what are we going to do with that? This reference level is limited. These resistors are going to resist current through here. So if we tried to draw an amp through here, we wouldn't get it. The voltage level would sag because this resistor, when you tried to pull an amp through here at 2.5 volts, you're going through a 10K resistor. Now you could lower this resistor, but another important thing to remember is that everything is a temperature sensor, including resistors. Resistors have temperature-dependent noise, and that gets worse the more current you draw through them. So, oh, thank you, Matt. I'm glad that's a little better. I will try to stay more zoomed in. Please call me out if I don't. So, this will give us a reference, and I'm going to call it reference for LC, reference low current. Okay. It's a fine reference voltage, but you don't want to draw a lot of current through it. So what can we do with that? We need current. We need to be able to move these signals around without drawing our power rail down or changing the reference voltage. It's extremely important that we don't change the reference voltage. What we can do is use the op amp in what's called a voltage follower mode. And I'm probably going to wire this up exactly backwards. So we're going to look it up. Op amp voltage follower circuit. There we go. Did I get it right? I even got it right. Perfect. So, op amps are beyond the scope for today because I am not smart enough to talk about op amps. Why is Walt Disney telling me about terms of use? Fine. But op amps have an inverting and a non-inverting output. So, the short version is, if this signal is higher than this one, it is going to boost the output. If the positive signal is higher than the negative signal, it is going to increase the output voltage. If the reverse is true, if the negative signal is higher than the positive signal, it is going to decrease the output voltage. So this is a nice simple case because we're hoping our reference voltage here is constant. But what does that give us? It means that if we put 2.5 volts into here, if this is lower than 2.5 volts, it's going to rise up within the limits of the power rails as much as it can until these two values are equal. So, since we've wired the output directly into the inverting input, the op amp is going to do everything in its power to make sure that these two voltages are equal, which means the output voltage has to be equal to the reference voltage. Op amps are, impedance is a thing I am not smart enough to talk about, but the op amp inputs are very low impedance. They do not draw much current. The op amp, I'm sorry, they are very high impedance. I can't believe I said that. High impedance. They do not draw much current. They impede the flow of current. They reference the voltage without drawing much current. And the op amp specifications will call that out. If we look somewhere in here, maybe at the top level, maybe further down, if we search for open load, output and impedance versus frequency. Does it even say what the input? Okay, I'm not seeing it. The input impedance is frequently on the order of like mega ohms, right? The ideal op amp that like we design around and then doesn't exist is infinite input impedance. Okay? And the ideal op amp output is zero output impedance. So zero input. Getting distracted with data sheets. And Matt, you asked about the difference between the input and the output rails. The datasheet here calls out the absolute maximum ratings for voltage. For the input voltage is the negative rail minus 0.5 volts and the positive rail plus 0.5 volts. If you've never run into them before, absolute maximum ratings are what it does what it says on the tin. Exceeding these values will damage the device. It does not guarantee the device will work to those voltages. It guarantees that going beyond those voltages will damage the device. So if you went down to negative 0.5 volts on a zero referenced one of these op amps, you would damage it, almost certainly. Generally speaking, it will work pretty close to that, but not always. The current input here, absolute maximum, is 10 milliamps. So it will never draw more than 10 milliamps through its inputs. And let's see. Yeah, that's probably all the interesting things there. So I couldn't find the input impedance. I'm sure it's staring me right in the face. Typical characteristics. The output impedance is dependent on frequency, as many things in real life are, but the frequencies at the audio range, which are down below about 20 kilohertz if you're a young person and you have good hearing, or if you're me, maybe like 15 kilohertz, they're pretty flat. You'll see the gain characteristics and the impedance. Oh, they're doing open loop gain. That's fine. I thought I saw an impedance chart as well, but it's effectively the same because the gain is determined by the impedance. Okay, I'm going to stop looking at the data set and go back data sheet. Here we go. Open loop output impedance versus frequency. It does change with frequency. It's fairly flat, and all of these output impedances, like 1,000 ohms, 100 ohms, it's a log scale, so we're probably looking at about 20 ohms there, maybe 50. But down in the audio range, and this is specified as an audio op amp, this is pretty flat. And then it starts to get bad again up above 100 megahertz, which is not an audio frequency. So I don't know why you'd use this op amp for that. But phase reduce. Okay. So if you've never read a data sheet before, they're interesting, but it's definitely a matter of you will learn what you don't know in the data sheets. At least I learned what I don't know. So we have a reference voltage. How excellent. And the op amp can source some current for us. So we can actually use this reference voltage. It won't start drawing current through these resistors, so it won't get noisy. Wonderful. And you could probably do this circuit without using the op amp in voltage follower mode to get the second reference, or to get a better reference voltage. There's a principle in op amp design that I believe is true, or I've at least heard it from people who know way more than I do, is that especially in this package that has two op amps in it, you don't want to leave one of these unused. You want to at least pacify it and make sure it doesn't oscillate, because not connecting wires to it doesn't mean that there aren't signals there. It just means you haven't put any intentional signals there. And what do we call signals we didn't put in there intentionally? We call them noise. This op amp can start to oscillate if you don't use it. So you either want to like tie it down to ground everywhere, and there are documents on how to do this. Please don't take my like off the cuff tie it down to ground statement as exactly what you do. You go read the documents from TI and from your op amp manufacturer on how to pacify an op amp effectively and make sure it doesn't oscillate. Because otherwise it may pick up an oscillation. It may start picking up the radio station nearby and amplifying that, and then all of a sudden you've got that radio station signal in your op amp, and these two things are micrometers apart, right? So the odds of a little bit of that signal getting into here become very, very high, and that results in noise. So we've got our reference voltage, and the goal here is to move the input signal from the microphone around that reference voltage. We want to block the low frequency static voltage offset on it. So what did we say was a good thing for blocking low frequencies and passing higher frequencies? Well, we use a capacitor for that. So we can take a capacitor here, and I'm going to have to look and see what I used. So apologies if I hit the microphone with my head. I used a 475. So the capacitor that's in there right now is labeled 475. The way that works is the 5 is an exponent, so it's 5 zeros, and this is picofarads. Everything on these kind of capacitors, ceramic caps, tends to be referenced to picofarads because the values tend to be very, very small. So because that is irritating and I can't think in picos, this becomes that many nanofarads, right? 47,000 nanofarads, or 4.7 microfarads, which is the way I'm able to think about it. So I did the math when I put this first together, and nothing I'm doing here today is original. Everybody and their brother has put together a headphone or a microphone amplifier and done it better than me. But this is mine, and you can't take it away. And all its problems are mine. So the signal coming out of here is unreferenced. We've blocked that portion that wants to put it around ground, but we have to give it something to be around, or it'll just float around as, again, signals float through the air. So by giving it this reference voltage, we take our sine wave and we move it so that it's centered around this reference voltage. To put it another way, this signal here is a very low impedance reference at 2.5 volts. If this capacitor weren't here, it would provide a bunch of amps out to the microphone, which would flow back through the coil, smoke the coil in the process, of course, because it's a sensitive dynamic microphone, and flow back to ground. But this capacitor blocks that 2.5 volts at however many amps would flow, right? Some low resistance. But it doesn't block the higher frequency components. And the higher frequency components In this case, higher frequency being 10 hertz and up, let's say. And we could do the math on it, but I'm not going to because I would be doing math on the internet, and good Lord knows nobody wants to see that. So we've taken our signal and passed it through this capacitor and re-referenced it to ground. And now we've got that same signal minus the very low frequency components. And remember, DC is just a low frequency component with an interval of 0, right? It has no periodicity to it. So it gets blocked. It's now our alternating current signal of microphone output referenced to 2.5 volts. Cool. So we now have a signal that is useful to us in this circuit. It's halfway between 5 volts and ground, and that means we can safely pass it into our op amp. I think that's kind of cool. So what are we going to do with that signal? Well, I'm going to reference back to the actual circuit that I did. So the way op amps work, or the way op amps are frequently used in an amplifying way, is with feedback. And the way that works is kind of cool, I think. So let's copy this, move this down. And I'm reverse engineering my work here from what I built already. One incredibly useful thing, oh my goodness, thank all the smart people, is that op amps, especially 8-pin op amps, have a very standard pinout. This is always the negative rail. This is always the positive rail. Output A, inverting input A, non-inverting input A. Output B, inverting input B, non-inverting output input B. So you'll note, first of all, it's always non-inverting, inverting output, non-inverting, inverting output, moving from the back of the chip to the front of the chip. Positive rail on one side, negative rail on the other. And this was designed by people way smarter than me for all kinds of reasons I couldn't begin to theorize. My goodness, excuse me. About. I'm sure that putting these power rails here, A, it makes it standard with a lot of other components so that you know what you're getting into. It minimizes crosstalk between these signals. It puts the output close to the inverting input. And that's actually really interesting. Generally speaking, there are places where this is not true, but generally speaking, all op amp circuits have to use feedback, and you almost always use negative feedback. This is an extreme example. We have wired the output directly to the input. Why have we done that? Say we tied this to ground and we put a signal in here. This op amp would immediately try to output a voltage that would make these two inputs equal, but we haven't connected them. We left these disconnected, so this goes to ground now. No matter what it outputs here, it cannot make these equal. It's impossible because we have provided no feedback for it. So it is going to immediately crash into the positive supply rail and stick there. And it's going to be noisy, and it's probably going to start oscillating. And oscillating kills op amps, and it certainly kills your signal integrity. So when we provide this negative feedback, again, this is an extreme case because we've got no resistance in here. We're just saying we want the output equal to the input. As soon as the output starts to rise, this negative input starts to rise. And so the difference between them becomes smaller and smaller, and the op amp stabilizes. And if somehow the output goes above the input, that will cause this to be higher than this, and it will cause the output to drop, right? So this extreme no resistance negative feedback scenario is one that provides no gain. It's unity gain, and I'll explain how that works in a second. I think I said earlier I wasn't going to explain that, and I probably shouldn't, but I'm going to give it a shot. But it it stabilizes the op amp. Almost all op amp circuits use negative feedback, and we're about to do it here as well. So what are we going to do? And again, I'm referencing my little circuit here. So we need a power rail. And which one do we use? We use ground. Perfect. That's what I thought. Right? Right? Ah, no. No. We're going to use our reference voltage as this. This is going to result in some phase inversion. Somebody's probably yelling. Somebody who knows way more than I do and should be doing this stream instead is probably yelling at their screen about the phase inversion. Yes, I know. It's an audio signal. I do not care. Okay. So with that out of the way, and if you're yelling at your screen and you know better, please post in comments. I'd love to know why this doesn't work well. But most op amp stages, again, I'm extrapolating from what I've read. You can't see me. I'm waving at my pile of books. Most op amp stages are inverting. If you want to not invert your signal, you'll usually use 2, so you'll invert it and then not invert it back. Non-inverting op amps have gain limitations that inverting op amps don't have. So, with that out of the way, we are going to do this. And we're even going to click on the things that we want to click on. So what on earth are we doing? Well, we're wiring up our input to our audio signal, for starters. We're going through a resistor. Okay, that seems kind of weird. We want this signal. We don't want to resist it. And we've also got a resistor on our output here. What's going on there? Well, what's going on there is we have to provide that negative feedback, right? Otherwise, the op amp's going to oscillate and go straight to hell. And that's not what we want. So we've got a resistor between the output and the input, the inverting input. And we've got just our reference voltage into the positive. Okay. The reason for this is we're just going to say, okay, if this signal is higher than this, I want a lower input voltage. So if the signal is above our reference, above 2.5, we got more signal from the microphone than 2.5 volts, than ground on the microphone side of these things. Then I want a negative voltage out here, not negative exactly, but negative relative to the reference. So something below 2.5 volts. And vice versa, if it's below our 2.5 volts, then this will be higher, and we will get a signal that's higher than 2.5 volts here. Why do we have these resistors? The ratio of these resistors to each other determines our gain factor. So let's take an extreme example and say we made both of these 1. I'm going to find my little reference card here so that I don't screw this up, because I think it has, we'll type this in here. So the gain of an inverting op amp setup is negative R2 divided by R1. So it's negative because it's an inverting setup. And in this formula, of course, this is R1 and this is R2. Okay, R2 is the feedback resistor, R1 is the input resistor. And frequently when this is drawn, this gets flipped upside down. The op amp signals are drawn like kind of willy-nilly depending on which way you want to reference it. I find that extremely confusing and I'll screw it up. So I'm sorry, I'm dumb. for all the people who this is going to drive nuts, but that's just the way it's going to have to be today. And that screwed up. Delete that horizontal wire. Okay, perfect. Kind of move everything closer together here so that we can see a little better. So in this case, R1 is 1, R2 is 1, 1 divided by 1 is 1, -1, our gain is -1. So a signal coming in just gets inverted. It gets flipped around our reference voltage and then output here. And that output then will flow back through this resistor, nullify the input signal, and the op amp is happy. These two inputs will be at the same voltage. But, you know, this is kind of useful, but not super useful, because it would be nice to get some gain out of this. We did order a part called an operational amplifier after all. And that means that we probably want to amplify something. So I'm trying to see the resistors that I've used, because I determined these experimentally more than a month ago. And okay. And now, you know, my brain just isn't so good. So the higher this value is, sorry, I like to edit it here in the symbol properties. It makes it more clear to me. So if we made this 10 kilo ohms now, and we left this 1 ohm, now we're going to get 10,000 times inverting gain out of this, right? This is 10,000 times larger than this. R2 becomes 10,000, R1 is 1, -10,000. We're inverting at 10,000 times. That is a completely reasonable way to use an op amp. In this case, that is a little too much gain. So I set this to 2.1. Nope, I think I've got a 210 in there. So what have we got then? Our gain is -10,000 divided by 210. So what is our gain? Do I have a calculator running? Not yet. 47.6 times. Wrong window. So our gain here is -47.6. So where does that leave us? Well, we talked earlier about our input signals, right? So our input signal, my input signal right now is in millivolts, right? We're talking about this dynamic microphone. Its absolute maximum numbers are like 50 millivolts. And that's like Obama mic drop on the stage, which probably destroys the microphone when you do that, for the record. Please don't ever drop a real microphone. Oh my God. Nobody should drop a microphone. I'm not picking on Obama. I'm saying nobody should drop a microphone. So 50 millivolts, right? So 50 millivolts times 47 gets us around 2.3 volts. So, and we're talking absolute maximums here. So if somehow you got 50 millivolts out of this dynamic microphone by screaming into it, your favorite heavy metal band, or you know, Brothers of Metal singing Power Snake, or whatever you prefer, you will get 50 millivolts out of the mic. Our 47 times gain, you'll get 2.35 volts out. So where does that leave us? Well, our power rails are 2.5 volts away from our reference, right? We've got our reference here, and it's at 2.5 volts, but our power rails are at 0 and 5. So even if we go 2.35 volts away from 2.5 volts, we haven't hit our power rails. Even if I do my best, you know, Nightwish imitation over here, and try to hit those frequencies that I can't hit at all because I'm a middle-aged man, I won't come anywhere near my power rails. And that was the key. That's one of the key factors here. Of the output of this circuit can't hit those power rails or will start distorting. In the same way that and remember, this is all upstream of the computer, right? This isn't a digital signal where the analog to digital converter in the computer runs out of numbers. But the effect is very similar, where the analog circuitry hits the power rails and you start distorting and clipping. It just tends to be a little nastier in the analog domain. And also you can start the op-amp oscillating, which then everything goes to hell. And you can destroy the op-amp. So we've got our 47.6 times gain set up. We've got our feedback network set up here. And we've got our output signal. Okay. We're actually, believe it or not, pretty close to done. So this circuit is all referenced to our power supply that we've plugged in here, 5 volts and ground. And that 5 volts and ground is coming off, in my case, a very cheap cell phone circuit, right? A cell phone power supply. Cool. Totally fine. It's not noisy enough for me to notice anyway. I hope it's not noisy enough for you to notice either. This is going to get plugged into maybe my computer, maybe my radio, maybe my cell phone, right? There's not just one ground in the world. We use the word ground as though it means something, and unless you go out and you hammer a stake into the ground, you don't really have a ground reference. You've got something we call zero, and we call it ground in circuits for convenience, for kind of a reference to zero, and it's made up. You know, the power supply on the far side of this barrel jack might be a transformer. It's probably a switching power supply in today's day and age. If you can lift up the little plastic box and not think, oh goodness, that's heavy, it doesn't have a transformer in it, or at least not one of any significance. So it's probably referenced to something, maybe to mains earth, which may or may not be ground, all kinds of things. So we want to output our signal again in a way, pardon me, I should have been faster on the mute there, in a way that doesn't mess up the computer. If you're into audio or have done much of it, you've probably run into ground loops. I have not done much audio, so I apologize in advance if I say something extremely stupid. But the ground that's coming in from the computer here on the shield of this 3.5 millimeter cable, or 1/4 inch if I get really motivated, and the signal going out to the computer are both kind of referenced to each other. They need to be relative to each other, but they don't need to be relative to anything in my circuit, right? I care that these two voltages are 5 volts apart. This ground may be 10 volts above what the computer has, and that's okay if that happens. So one component that you can use to deal with that, we kind of did that over here with a capacitor, and you can kind of do similar things. One way to do that is to use an audio transformer. Or a transformer. An audio transformer is just like the cheap and easy way to do it because these transformers are in everything. They are literally a few cents a piece, even in fairly low quantities. And they all perform the same goal. So this audio transformer is going to want the signal in on one side, right? The way the transformer works is by converting to the magnetic domain at the end of the day, right? So we want current to flow back and forth through here in such a way that it sets a magnetic field that induces the same current in the other side of the coils between this ground and this signal line, right? as long as they move relative to each other, we don't care, by the same amount that they move over here. So what's our reference over here? Well, if I look, I hope my reference should be our reference frame. I'm actually not wiring it up quite the way that I've got the actual circuit wired up, but I can't mess with the circuit right now because I'm talking to you. So after I'm done, I will go back through and see if I can get rid of some of the cruft that I built into this circuit. At the moment, I have this style voltage reference in several places that I believe I don't need. But I am doing this right. Actually, what I'm doing is grab. Added a capacitor in here. What is this value? It's probably the same. I just touched it. I apologize for that. It has definitely not. Give me a second, please. All right. The irritating almost a minute lag here between me speaking and hearing myself back on YouTube on the tablet that I'm listening on makes it really hard to know if this is fixed, but I believe it's fixed. Let's just give it a second. There we go. That sounds a little better. So let that be a lesson to any aspiring electronics YouTubers. Don't touch the circuit that you're actually recording your microphone through. It's certainly not the best. Also, I should probably set up a better monitoring setup, but that's to be done later. So the value on that capacitor is 106. So 10 and then 6 zeros. So that's nanofarads now. Get rid of 3 more zeros. That's microfarads. So it's 10 microfarads. Again, just as a DC block, right? So this circuit now, double checking my audio one more time. This circuit now is basically complete if I don't need to change my references, which, as I said, I'll test after we get off the air today. So we've got, let's kind of take an overview here. We've got a signal coming in that's referenced around ground. We block the DC components out. I've got something going on here with the wires that needs to be cleared up. I see. Clear that horizontal wire out. That would definitely have been unfortunate. So the signal's coming in reference to ground. We block out DC components with a 4.7 microfarad cap. We reference it to our 2.5 volt, hopefully very stable op-amp supplied 2.5 volts. We run it through a 210 ohm resistor to provide some input resistance with a 10 kilo ohm feedback resistor to get us our 47.6 times gain, inverting, negative. We take the output of that, run it through a transformer, back referenced again to this 2.5 volts, because all our audio is around 2.5 volts in this circuit. And then the other side of that transformer is hooked up to our output. So good Lord, I've been talking for, what, an hour and a half, and this is really the meat of everything right here. We'll move him over a little bit so that it's a little easier to see. We can probably fit the whole thing almost on the screen. And if I move the power block around just a little bit, we can fit everything. So hopefully at a reasonable zoom level there, that is the whole deal. We're just going to use one stage of an op-amp to get us 47 times gain, another one to get us a reference voltage, and a transformer to isolate us from the PC's ground, to make sure we don't get any ground loops or anything like that. So, what else is left to do? Well, I've kind of done the interesting part, and then it's the boring part. And I don't know how much I'll get through today, but we'll see. Because as quarantine goes on and everything else, of course, I've got video calls with friends and family today to just kind of make sure everybody's doing okay, and I hope you're all doing okay, and checking in on each other and keeping an eye on your friends. So what's left? Well, to build, this is a wonderful schematic, but it doesn't represent reality at all. Reality is copper and components. So in KiCad, to do that, to go from here to there, we need to annotate our symbols, which will take the entire schematic page and assign references to it. So right now, everything's like R question mark, U question mark, T question mark, all these things, right? Which isn't helpful, because like, is this resistor the same as this resistor? Or are these two the same two halves of the same op amp, or is there another op amp involved? Let's see how we go. So we're going to annotate, and KiCad, I said it wrong again, helpfully just gives us letters and numbers for everything, right? Our R1 in this equation up here became R3, and R4 kind of does a left to right, top to bottom thing. In that annotation dialog, there are better ways to do it. Let's see. Sort components by Y position. I think I prefer that. Clear annotations, and annotate. There we go. This gets us R1 and R2. And given that our formula here references R1 and R2, that's a little better for me. We've still got, these are all U1 components. U1A, U1B, U1C. We've got our barrel jacks, mic in, mic out, and barrel jack there, and a bunch of capacitors for various things. Blocking caps up here, a little bulk capacitance for the power supply, and then a decoupling cap. An important thing to note about schematics, and this threw me off for a long time when I got started in this, is that like this capacitor is actually very important, that it's very close to these power rails. But the schematic doesn't reflect reality. It's not intended to. It's intended to clearly explain the function of the circuit, which is why I kind of kept all the power stuff out of the way. The power stuff is very important, but it can go together somewhere out of the way, and beyond that, we can just assume we've got a 5-volt reference somewhere, right? And in fact, in most places, we don't even need the 5-volt reference. We need our reference tag here, which I didn't explain. These labels are just everything with the same name is connected to everything else. it's the same as the power symbols, right? All these plus 5-volt symbols are all going to get tied together by the software, but they don't need to be close together to explain the intent. And you can kind of see here, we've got different sections going on, but this is just a voltage reference section. This is just a power connection. Everything that matters is up here. So if we got the other parts right, we can assume that they're right and move on with our lives. So we've annotated. The next fun and extremely irritating part, for me at least, is assigning footprints. So it knows J1 is this 4-pin jack that I've created, but it doesn't know what it actually looks like in the world. It's not, the schematic symbol here doesn't bear any resemblance to the thing that I've actually got that will go onto the circuit board. To do that, I've got to come find the right symbol, and I believe it's this one. And it's going to make me go through each of these components and tell it what kind of a component it is. So if we look through here, search, no, we cannot search. We've got our barrel jack that a lot of these connectors the extremely good community has put together, and there are a ton of them, and they're wonderful, and I love them so much, but they can be hard to find unless you use them all the time. So I'm going to have to go through and compare it to my inventory and see what I've got for my barrel jack, right? Because there isn't just one barrel jack. If we go to DigiKey, we give us a larger window, we go to DigiKey, who's just my current favorite, and we search for a 2.5 millimeter barrel jack. There isn't just one manufacturer. Barrel Jacks Incorporated does not exist. Barrel power connectors, probably what I want. Yeah, let's look here. So 30 items. So, okay, here's 5 manufacturers, different packaging types, different series types. We want something that's in stock because I'd like it before I die. Oh, and we've got the male side. Okay, yes, we've got what we want here. That's right. So there are different forms: 2 conductors, 2 contacts, 2 conductors, 3 contacts, which provides indication of if anything's plugged in. Not particularly useful in our case because this is power. Nothing's running if it's not plugged in. But if you were using this for another signal, you might want to know if anything was plugged in there. Or you can use this for switching between like a battery power supply and a wall wart. There are generally better ways to do that, I think. But so we're going to look for the 2.5 millimeter inner diameter. We're going to apply some filters here. We're going to want the jack side of things rather than the plug side of things. And here are some different options. And that's similar to what I have, but that one's actually cut away. That's interesting. Here's some panel mount versions, which is not what I want. I want the board mount version. So it's going to take me a little bit to go through my inventory, go over to my Stanley organization cases, find what I've got, find a good footprint. And if I'm not able to find a good footprint, I'm going to build one. You note that some of these connectors are in the BVH connectors MISC library. And we can take a quick look at that. View selected footprint. And this is one that I built, right? I ordered these connectors probably off DigiKey and went through its data sheet and built this whole thing so that I could use that connector. And it's a distressing, it's one of those things, when you move from one industry to another, there's always, some people like to call them impedance mismatches, right? I'm a software developer by day. So my first approach to everything is to go look for a library for something. Now I'm a mobile software developer, so it's not quite like Ruby or some of the server environments where, good Lord, you need a library if you're going to write a left trim or something like that. Not to reference something in the past that caused a lot of people pain. Sorry about that. But I'm sorry, it was left pad, wasn't it? Anyway, so I'm used to a lot of these resources being provided, but that's simply not the case in electronics. You just need to go through and you need to make sure you're accurate. These holes that go into the board have to be where they are or the part won't line up. So I was talking about the joy of data sheets before. If there weren't a data sheet for this, you would go through these pin specifications and the mechanical and packaging information down here, and it would tell you exactly, here we go. Here is your part. Here is how many millimeters are between these pins. Here is how wide the part is. Here's, your recommended footprint. They will give you so much information that you didn't even ask for about stencil openings, example board layout, recommended solder mask setback, all these kinds of things. What plane is this foot going to lie in on this part? All these things. You actually need to understand those a little bit in order to get the footprints laid out. Because once we do that, and I'm going to jump ahead a little bit here, I've only laid out a couple of footprints. Let's do a few more. The op amp is going to be, let me look back at my earlier project here. Yes, this is the one. And, right? Yes, this is it. And let me look at what footprint I used for it. Nope, that's annotation. You want the footprints. Nope, that's annotation. Footprint editor. No, that's the wrong button again. I clicked the wrong button. End of the world. That takes me straight to VCU. Sure. Annotate first. This should have already been done on this project, but maybe I worked on it on a different machine. Yeah, that's entirely possible. So I don't want to save those changes, but interesting. Why is this not annotated? It is annotated. Well, I guess I just annotated it. Changes. Let's go back to that KiCad instance. Is that the one? Nope, other one. Let's go here, go here again and see if it is definitely not right. Yeah, it's definitely not right. Anyway, should be able though to go to the circuit board. Layout editor. Ah, interesting. This must be on an entirely different machine. Oh, I haven't done layout on this one yet. I'm sorry. That's why it hasn't been assigned, because I haven't done the work yet. So I need to find the right footprint for my op amp, which luckily is a very standard package. Again, if we look back up here on the mechanical data here, one of the things it's going to provide up top, this is an SOIC 8-pin, right? Which I learned when I ordered them means extremely tiny, which is fine. It'll be fine to solder, but U1. I'm going to search over here for surface mount components, SMD packages, SP should have SOIC in here somewhere, I would have thought. And if not, we'll have to build it. Components, I wouldn't have built this one yet. Nope. So I'm not going to make you sit here and watch me as I assign these footprints because it's incredibly boring. But that's the next step. And after I do that, I may come back maybe later today, maybe another day, and do the layout for this board, or I may do that off camera and then just talk about it after it's done. It's kind of an interesting process, but it can also be very tedious of laying some things out, figuring out it doesn't work, moving things around, that kind of thing. And I've been rambling for like an hour and 45 minutes. You all probably have better things to do with your Sunday or Monday, depending on where in the world you are. And yeah, I think that's probably where I'm going to more or less wrap it up. I hope everyone's having a good Sunday. I hope things are okay in your part of the world and you're looking after your friends and loved ones. And maybe you learned something. And if you did, leave a comment or a like or whatever you like. If I did everything wrong, leave an informative comment. I'm learning as I go and always eager for more input. Anyway, I think I'll leave it there for today. I hope you all are doing well. And I'll say 73. Have a good one.